Hi guys, this is going to be a video on resonance, right? And so, as you're drawing molecules, you're eventually going to come across this phenomenon called resonance, where you don't quite know where the double bond should go, right? And so, what do I mean by that? Well, let's take an example of a molecule, right? Let's say we had SCN minus, right? This is called thiocyanate, right? It's a polyatomic ion and it has a charge, you notice, right? In general, charged molecules like these tend to have resonance, right? Tend to have resonance. And so let's first draw the structure, right? Let's get our element, our valence electrons, and the octet. So we have one sulfur, one carbon, one nitrogen, and we have a charge, right? Sulfur has 6 valence electrons, 2 in the octet. Carbon has 4 and 4, right? Nitrogen has 5 and 3. Of course, you can look up these values in the periodic table. For the charge, since it's a minus charge, that means there's an extra electron in the molecule, and it needs to lose it, right? In general, molecules tend to want to be at 0 charge, and so that's going to try and lose one of those electrons to somewhere, right? Okay, so let's tally this up. That's 6 plus 4 plus 5 plus 1. That's 16 total valence electrons. 2 plus 4 plus 3 is 9, minus 1 is 8 bonding electrons, right? So that tells us there are 4 covalent bonds and 8 non-bonding electrons, right? So now we got to figure out, all right, how do we actually draw this molecule? Well, there's a lot of options, right? There's a lot of options. We can draw it like this, right? Where we have the valence electrons like distributed as such. We can draw it like this. We can draw it like this. We can draw it like uh, this, right? There's a lot of different options here, right? There's a lot of different options here. Now you might wonder, well, are these isomers? Well, some of them are considered isomers because the arrangement of the bonds have changed. For example, this has nitrogen in the center, and it's bonded like so. So in this structure, we have sulfur bonded to nitrogen and carbon bonded to nitrogen. But in this structure, we don't have sulfur bonded to nitrogen. So we know that those are isomers. However, if we look at just these structures here, right, these are considered resonance structures. The placement of the atoms hasn't changed, it's the bonds between them that have changed. Okay? And so, what is resonance? Well, resonance represents this movement of electrons from bonding orbitals, right, bonds, to non bonding orbitals, right? So, how do we represent that? Well, we represent it like so, okay? Where we have all of these different options for the bonds between those atoms, right? And so if we take a look at SCN minus, okay, SCN minus, well, we have to figure out, well, what is the best resonance structure for this molecule, right? In general, in general, there are some principles that we should follow when we're constructing good resonance structures, right? One, we want to put the most positive atom in the center. Okay, the most positive atom in the center, right? That allows the electrons to, have a place to, put their electrons. And so if we look at this molecule here, all of these different options, well, you could put either carbon, sulfur, or nitrogen in the center. Well, the most electropositive atom is going to be carbon, right? And if you look in the periodic table, you have nitrogen, sulfur, and carbon, right? Well, decreasing, well, you know that electronegativity increases this way. So that means electronegativity decreases going this way, right? And so the element that is most to the left and most up and most downwards, right, is going to be carbon. You might be wondering, well, what about sulfur? Well, going downwards doesn't really change um, all too much, right? So sulfur is pretty electronegative. So carbon is going to want to be at the center. Okay, so we're going to put carbon at the center. All right. Now, if we try bonding nitrogen and sulfur to it, it actually doesn't matter if we flip the positions of sulfur and nitrogen, right? Um, it's just the same as like mirroring the molecule. Okay, so we don't have to worry too much about that. So, most positive atom in the center, 2, we want to minimize the formal charge. So, formal charge should be minimized. What is formal charge? Well, formal charge is this idea that the electron distribution across the molecule should generally match the atoms, right? And that's number 3, right? Formal charge should match the electronegativities. Okay. So if we look at these combinations, right, and I'm going to draw just a few of them. So we can have triple bond between the sulfur and the nitrogen. We have double bonds between them, or a single bond between the sulfur and carbon, and then a triple bond there, right? And I'll put the valence electrons where needed. Okay. Well, how do we calculate the formal charge? Well, formal charge on an element is equal to the total number of non-bonding electrons, plus 1/2 the number of covalent bonds. Okay, so total non-bonding plus half the number of bonding electrons, right? And so visually, we can actually calculate this by putting a little box around our elements, right? So I'm going to put a box around this sulfur. Okay. And the box should encapsulate all of the non bonding electrons. And then to represent half of the covalent bonds, I'm going to cut the covalent bonds in half. Right. So inside of this box, we have 5 electrons. Right. So 5 boxed electrons. So normally, right. And so the formal charge is going to be um, what the element has normally. So normally minus the boxed electrons. So formal charge is equal to the normal amount of valence electrons minus the boxed valence electrons, right? And so if we look at this sulfur, that'll be 6 valence electrons normally as an element minus 5. So this has a plus charge on the sulfur here. Okay. If we calculate it on the carbon, that's 4 minus 4, or a 0 formal charge there. And finally, this nitrogen over here has 7 boxed electrons, where it normally has 6, so we know that it has an extra electron. So there's a -1 formal charge over here. Okay, so I'm not going to draw the box for that. It gets a little cluttered, but visually you can kind of see that. Okay, so if we look at the formal charges between these structures, the formal charges should be minimized, as in as close to 0 as possible, and the formal charge should match the electronegativity. Okay. Right. So if we look at this structure here, 0, 0, um, -1. Sorry, miscalculated the formal charge here. That's actually a -2. Okay. So 0, 0, -1. So always the formal charges should always add up to the total charge of the molecule, right? So there's a -1 charge here, so the total formal charges should add up to a -1, right? Anyway, right, so 0, 0, -1, and if we look down here, this has an extra electron, so -1, 0, 0. Okay, so minimize the formal charges as close to 0 as possible. Well, if we look at this structure, just looking at the formal charges, disregarding the fact that they're positive and negative, we have 1 plus 2, or 3 total formal charges, right? 3 formal charges. This structure here only has 1 formal charge. This structure here only has 1 formal charge, right? So we know that this structure is going to be pretty bad. So let's cross that out. That's not going to be one of the resonance structures that contribute to this atom. All right. So how do we determine between these two? Well, that's going to be number 3. Formal charge should match the electronegativity. We know that nitrogen is more electronegative than sulfur. Okay? And sulfur is more electronegative than carbon. So let's place the electronegativity, the formal charge, the minus charge, on the nitrogen. This is most likely going to be the best structure here. Okay? Now, one caveat here is that sulfur and nitrogen are actually very close in electronegativity, and so both of them are going to be contributing, but it doesn't particularly matter for this example. Okay. One final thing to note, right? One way we can represent right, as I said, the resonance was this movement of electrons from bonding orbitals to non-bonding orbitals. And so if we take a look at those two resonance structures, where we had electrons like this, and then electrons like this, right? Well, if we look at the bonds, we notice that we gained a triple bond over here. We lost a double bond over here. Well, that's because one of the lone pairs moved into the bond, right? And so if we just leave it like this, carbon has too many bonds coming out of it, you see, right? There's 5 bonds coming out of it. So one of those bonds is going to then move to sulfur and become non-bonding electrons. Okay? Similarly, to get back to that structure, the electrons can move this way, right? And so you can kind of see how the electrons are kind of being shuffled around between non-bonding orbitals and bonding orbitals. Okay? So, and that here would represent the resonance in this molecule, right? So hopefully that helps. Take care.